This problem, the setup looks very similar to the problem 110. However, what's going on in the apparatus is totally different. In problem 110 in this chapter, there's no reaction occurring between helium and neon. But in here, you can see we have a nitric oxide NO react with molecular oxygen, NO with oxygen at these reactions. And in this apparatus, we have NO with 4.0 liter and 0.500 atmosphere, and oxygen 2.00 liter and 1.00 atmosphere, separated. Once this valve gets opened, NO will effuse through and oxygen will effuse through, and they will react immediately through these reactions. Because both NO and oxygen are gas, we know the temperature, volume, and pressure. We can calculate the Mohr number, and because we have the Mohr number for both NO and O2, we need to determine which one is the limiting reagent. Then we can figure out what is remaining after the reaction and determine the gas remain at the end and calculate their partial pressures. Okay? Now first let's calculate the Mohr number of each species. First, the Mohr number of NO, N equal to, according to ideal gas law, the pressure of NO times volume of NO divided by the ideal gas constant and temperature. And we know that the pressure for NO at the beginning is 0.500 atmosphere, and the volume is 4.00 liter, and temperature is 25 Celsius. We need to convert it to Kelvin. So we have 0.500 atm times 4.00 liter divided by ideal gas constant 0.0821 liter atmosphere over Kelvin mole times temperature, that is 25 plus 273.15 Kelvin. We have 0.0817 mole. That is for nitric oxide NO. And for oxygen, very similar. We have oxygen, pressure of oxygen 1.00 atmosphere, and volume 2.00 liter. That is the partial pressure of oxygen, volume of oxygen over RT. And we have 1.00 atmosphere for oxygen, 2.00 liter over R, 0.0821 liter atm over Kelvin mole times 298.15 Kelvin. We give exactly the same number, 817 mole. Now we have the Mohr number for both reactant. We need to determine which one's the limiting reagent. So we see, okay, to react with 0.0817 mole of nitric oxide NO. How many mole of O2 we need? That will be the Mohr number of NO times 2 mole of NO corresponding to 1 mole of O2. For every 2 mole of NO corresponding to 1 mole of O2, we have 0.0817 mole times 1 over 2, and give us 0.0409 mole of O2. This is actually smaller than 0.0817 mole of oxygen. That was right here. We have 0.0817 more of oxygen. We just need 0.0409 more of oxygen. Therefore, NO is a limiting reagent. Just write it. NO is the limiting reagent. Okay. Now let's use our initial, change, and final table to figure out what is remaining. So here is the reaction. I'll write it out. Nitric oxide react with oxygen. We have nitrogen dioxide. So initially we have 0.0817 mole of nitric oxide. You see here, nitric oxide 0.0817 mole right here, and same thing for oxygen 0.0871 mole of oxygen over there, 17 mole, and 0 mole of product, nitrogen dioxide. So because nitric oxide is the limiting reagent, it will be consumed completely, and for oxygen it will be consumed 0.0409 mole of oxygen will be reacted, and for the nitrogen dioxide 0.0817 mole will be produced. So in the final state we have 0 mole of nitric oxide, limiting reagent. We have 0.0408 mole of oxygen remaining, and 0.0817 mole of nitrogen dioxide remaining. So this is the final product. This is in the final state. We have so many more of oxygen, so many more of nitric oxide in this whole tank container with the volume 4.00 liter plus 2.00 liter, which is 6.00 liter. Now we have the mole number of each gas, we have the temperature, we have the total volume. We can calculate the pressure of each component now. So in the final state, the pressure of first nitrogen dioxide, we call it prime to refer to final, that is mole number of nitrogen dioxide prime times RT over volume. That's the total volume. So we have 0.0817 mole of nitrogen dioxide, 0.0821 ideal gas constant, and 298.15 Kelvin over 6.00 liter. We have 0.333 atmosphere for nitrogen dioxide, and for oxygen, that mole number of oxygen in the remaining part, RT over V, we have 0.0408 mole times 0.0812 liter atmosphere Kelvin mole times 298.15 Kelvin over 6.00 liter gave us 0.166 atmosphere. Okay, that's the end of the problem.